Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics in the chapters of mechanical actions and equilibrium of a body. This exercise was a previous one in the brevet exams in 2005 first session, third exercise. The title of this exercise is tension of a spring. We have a spring R of free length L0 is equal to 0.2 meters. And of stiffness K is equal to 100 newtons per meter. We fix the extremity O of R to a support and we suspend it to its free extremity A ball of mass M is equal to 0.6 kilograms. And of center of gravity G, see the figure. Then they mention the figure, now we can use it. Number 1. The two forces exerted on the ball are its weight W and the tension T of the spring. In part A, specify whether each of the two forces is a contact force or an action at a distance. We know that the only three forces that act at a distance are the weight, the electric, the magnetic. Then the W, the weight, is classified as action at a distance. And all other forces are classified as contact forces, in particular the tension T. So T is a contact force. Now in part B they are telling me to calculate the value of W vector. So here the value of W vector, they mean the magnitude. Take G is equal to 10 newtons per kilogram. Then the magnitude of the weight W vector can be calculated using the formula weight is equal to mass multiplied by gravity. Now the value of M is given by 0.6 and the value of G is given by 10. Plugging this on the calculator, it will give me 6. Since both M and G are in the SI, so the value of the weight will be in the SI, which is in newtons. So W is equal to 6 newtons. Now in part C they are telling me to state the other characteristics of the W vector. Then in part B we have stated the magnitude of the weight vector W. It's left to state the point of application. The line of action. And the direction. The magnitude is already stated in part B. Now because it is an action at a distance, then the point of application will be the center of gravity G. And we know that the weight always acts on any object having a mass vertically downward, then the line of action is vertical and the direction is downward. Now 2, they are telling me for a length L is equal to 0.25 meters of the spring R. So here the length represents the final length of the spring when the solid S being suspended or connected to the spring at the point A. So here L represents the final length of the spring, which is given by 0.25 meters. Now let me make some space here. So we are in part 2. Calculate by applying Hooke's law the value of the tension T. So we need to apply Hooke's law in order to determine the magnitude of the tension T. Then let's say apply Hooke's law. Always in physics we need to mention the law that we are using. And the law is given by that the tension T is equal to the stiffness K multiplied by the elongation delta L. Now the stiffness K is given by 100 newtons per meter. Delta L can be determined because we know the initial length and we know the final length. Delta L is given by the final length minus the initial length. Now the final length is given by 0.25, which is in the SI, minus the initial length, which is given by 0.2. Plugging this on the calculator, it will give me 0.05. Since both L0 and L are in the SI, so the value of delta L will be in the SI, which is meters. Then the elongation in this case is given by delta L is equal to 0.05 meters. Now we know the elongation and we know the stiffness of the spring K. Then we can calculate the magnitude, which is given by K multiplied by delta L. Now K given by 100 and delta L by 0.05. Plugging this on the calculator, it will give me 5. Since both K and delta R are in the SI, so the value of T will be in the SI, which is in newtons. Then the magnitude of the tension T is given by 5 newtons. Now here, in part 1, the magnitude of the weight was given by 6 newtons, and here the magnitude of the tension is given by 5 newtons. Now part B, they are telling me to state the other characteristics of T, and they are given by the point of application, the line of action, and the direction. Now, because T is classified as a contact force, then the point of application will be the point of contact between the two bodies that are at interaction, the solid S and the spring A. So it is the point of contact A. And we know that the direction, the line of action of the tension T is always along the string. And here along the string is given by vertically upward. So the line of action is vertical and the direction is upward. Now in part C, they are telling me to represent W and T with a scale of 2 newtons corresponding for 1 centimeter. So we are in part C. Now we know that each 1 centimeter corresponds to 2 newtons. And by represent, it means that we need to draw the vectors W and T. In order to draw the vectors W and T, we need to determine the length of this vector, because we know that rulers are graduated by centimeters and not by newtons. Let's start by determining the length of the vector W, which is given by corresponding for 6 newtons. Now if we crisscross 6 multiplied by 1 divided by 2, it will give me 3 centimeters. So let's suppose that this is the ball. So this is the solid S. So here they are not naming it to be S, okay. This is the point G, and this is the point A. Then we know that the weight W will be acting on this solid at the point G vertically downward. The length of this vector is given by 3 centimeters. So the name of this vector is W. Its length is given by 3 centimeters, worth of magnitude 6 newtons. Now we need to represent the vector T, knowing that its magnitude is given by 5 newtons. So each 1 centimeter corresponds to 2 newtons. What about the 5 newtons? Now if we crisscross 5 multiplied by 1 divided by 2, it will give us 2.5 centimeters. Then what does 2.5 centimeters represent? It represents the length of the vector A, which acts at the point A vertically upward along the string. So the name of this vector is T. The length of this vector is given by 2.5 centimeters, which is worth 5 newtons. Now here the vector W, so is given by 3 centimeters, 1, 2, 3. And the vector T of length 1, 2, 2.5 centimeters. Now in part D they are telling me the ball is not at equilibrium. Why? So notice that here both vectors W and T, they don't have the same magnitude. In order for the ball to be at equilibrium, both forces must have same line of action. Okay, here they have the same line of action. Opposite direction, they have opposite direction, but they don't have the same magnitude. So let's say since W and T don't have same magnitude, and this is because 60 newtons corresponding for the magnitude of the weight is different than 5 newtons, then the ball is not at equilibrium. Now in number 3 they are telling me the ball is still connected to the spring, is now in equilibrium. So we can make use of the condition of equilibrium. Determine with the justification the value of T in this case. So in other words, they are telling me that because we didn't change the ball, so the magnitude of the weight didn't change, but however now the ball being at equilibrium, the magnitude of the tension has a change. So we need to make use of the condition of equilibrium in order to determine the magnitude of the tension T instead of calculating it using Hooke's law. Then let's say at equilibrium, how do you apply this condition? So always on the left we write the sum of forces acting on the ball, and they are given by the weight plus the tension. And on the other side we write the zero vector corresponding for the condition of equilibrium, and we don't forget the vector over the zero. So moving T to the right hand side, so W is given by minus T vector. Now the first equation tells us that both forces acting on the ball cancel each other to give us the zero vector, whereas the other equation tells us that both W and T have the same line of action, opposite direction, and same magnitude. Since we are interested in calculating the magnitude or the value of T, which is the magnitude, then let's say in magnitude, now in magnitude weight is equal to the tension, so here we drop down the vectors and we remove the minus sign. But we know that the value of W didn't change, and this is because we didn't change the mass, which is given by 60 newtons. Then in this case, the value of the tension T is given by 60 newtons. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.